I'm thankful for the way that I'm feeling today. This is separate the digits in an array. So you're given an array of positive integers nums. You want to return an array answer that consists of the digits of each integer in nums after separating them in the same order they appear in nums. Huh? To separate the digits of an integer to get all of its digits it has in the same order. So if you had 10,921, well, what are the individual digits that encompass that number? Well, there's a 1, there's a 0, there's a 9, there's a 2, and there's a 1. So it splits up into 1, 0, 9, 2, and 1. Pretty short description, kind of confusing. A lot of different words. Kind of a significant amount of diction. It might be a little complex, but this is definitely one of those problems where you'll understand it better if you just look at an example, right? This is almost one of those problems where the input to output relationship is so simple that it's almost more intuitive to just look at an example than it is to actually read the problem description. Not advising that you do that in an interview, but just sometimes understand if you're reading the whole problem description or it's being read to you and you don't understand it all, don't necessarily panic, because the example might be a better exemplifying object. Okay, so if you had 13, 25, 83, 77, if you took this example, you have 13, 25, 83, and 77. Well, what you're essentially doing in this problem is you're just splitting up each integer into its single digit components and creating that new array and returning it. Meaning, if you had 13, what does that become? Well, 13 in its single components is 1 and 3. What does 25 become? 2 and 5. What does 83 become? 8 and 3. And what does 77 become? 7 and 7. And then we just return an array that is all of these things together, right? 2, 5, 8, 3, 7, 7. And that's what we return, right? So if you had a number, if you had a system like this, 1, 2, 3, 4, 5, 6, 7, right? Regardless of what it is, it's going to end up being 1, 1, 2, 3, 4, 5, 6, 7. So we're just taking an integer and we're breaking it up into the single digits that create that integer and returning that as a solution. So it's kind of like you're flattening, right? You're like creating a flat map of this array. At least that's how I kind of interpreted it. But interesting, right? So really, there's two things we need to think about when we solve this problem. The first thing is kind of like the fundamental data structure, not really data structure, but algorithm to process digits, right? So if you don't know how to do this problem, there's really kind of this trick that isn't exactly intuitive, but when it's learned, it becomes very easy to apply in these kind of problems, right? Whenever you're dealing with a problem where you have a number and you need to look at each digit within that number, right? Because in this problem, we have to do that. For example, when we have 13, right, we need to be able to look at each of the individual numbers to create 1, 3. So what's an efficient way of finding the individual digits of a number? Well, it depends on two different operations, right? If we take that number n and we wanted to figure out one digit of that number, let's say the last digit of the number. The last digit of a number is n mod 10, right? If you do n mod 10, this will give you we'll just put, this is last digit of number. All right. And if you did, so for example, right, if you did 13 mod 10, what this basically does is it tells you the remainder when you divide it by 10. So when you divide it by 10, you get 1 with 3 remaining. So this will give you 3. So notice how that gives you the last digit, which is 3. Now, that's only going to give you the last digit, right? Every time I mod this by 10, it's only going to give me the last digit. So if I want to get the digit that comes before it, right, the individual digit, I'm just trying to isolate to the individual digit, right? Because in order to solve this problem, we have to isolate the individual digits from the actual number. So if I want to isolate an individual digit from this number, I can mod it from 10, right? But if I want to isolate the next number, well, I can take this number, n, if I take n and I divide it by 10, floor divided by 10, this will remove the last digit, right? So these are kind of our two fundamental operations, n mod 10 and n floor divide 10. So how does that work? Well, if I wanted all the digits of 13, right, I could do 13 mod 10, and that will give me 3. And then if I did 13 floor divide 10, well, how many times does 10 go into 13? Once. That'll give me 1. And then if I did the remainder of that in modded by 10, I get 1. So here's our kind of all the digits we need to look at. Maybe do it a little bit more of a complicated problem, right? If I did 1, 2, 3, 4, 5, so that's 12,345. If I mod that by 10, what do I get? I get 5. And then if I take 1, 2, 3, 4, 5, and I divided it by 10, I get 1, 2, 3, 4. So then if I take 1, 2, 3, 4 and mod it by 10, I get 4. And if I do that again, 1, 2, 3, 4, floor divide by 10, I get 1, 2, 3. So if I did 1, 2, 3 and modded it by 10, I get 3. Right? So you notice how I'm just by following through this process, I can get each of the individual digits of a number. Right? So generally what you do is you just say, while the code, I guess, corresponding to do this, right? If I wanted to write this as a concise looping statement, right? I'm essentially saying while the number exists, right? While the number is greater than 0, we're going to print, I guess in this case, but we're going to have to save that information somehow, right? We print n mod 10, and then we take 10 and we set it equal to itself, floor divide by 10. Right? So this right here is like the standard code that you would write for looking at individual digits in a number, right? This would be the standard code to print individual digits of a number. So you need to like memorize this. You need to think about this, maybe walk through the modular arithmetic, walk through the floor division to realize exactly how this works. But this functionally is essentially what you need to understand in order to process individual digits of a number. Now, the only caveat of this is that it processes in reverse. Reverse meaning, you know, when we followed here, right, we did 1, 2, 3, 4, 5. But notice the first thing we printed was 5. Then the next thing we printed was 4. And the next thing we printed was 3. So we're actually processing this digit in reverse, right? If I was to print all of these numbers, I'd end up printing 5, then 4, then 3, then 2, then 1, right? So it's the reverse of what you actually want. So that means that, you know, if we did this for 13, we'd get 1, 3. If we did this for 2, 5, we'd get, if we did this for 1, 3, we'd get 3, 1. And if we did this for 2, 5, we get 5, 2 because it processes the number in reverse. So we'll just do that right now. So we want to look at each individual number, and what are we going to do with it? Well, we're going to append it to our solution. So we'll create this solution array, and we'll look at each num in nums, and then we'll just literally write this code verbatim. Okay, so we'll say while the num, okay, so I called it n, so we'll just call it n here, I guess. So while the num is greater than 0, we're going to add it to our solution, right? Because here we're trying to add it to our solution because each of the individual digits is one of the indexes of the new solution, right? For 13, 3 is its own digit and it has its own index. Every number has every individual digit has its own index associated, right? So we might as well append each individual number, we might as well append each individual digit to our solution. So instead of printing it, we'll just append it to the solution. And then we'll and then we'll set n equal to itself, floor divide by 10, right? So I'm basically, for each of the numbers, I'm walking through this process so that I can look at each individual digit that exists within each individual number. So I'm looking at each individual number and looking at each individual digit in each individual number, n. So then at the end, we just return sol, right? Now, remember I said that this is going to process numbers in reverse, right? So the problem here is it's close, but there's a little bit of an issue, which is, well, we have 31 instead of 13, right? Because it processes digits in reverse, because when you mod something, it gives you the last digit's value. So we have 31 and 52 and 38 and 77. So it's not exactly right, because it's close, because, you know, we have 13 and we have each of the individual digits, but they're not in the right spot. We have 25 and we have each of the individual digits, but 5 and 2 are in the wrong spot, right? They're flipped. So how do we deal with this? Well, we could, you know, play some tricks of like putting something somewhere and then flipping. But I think the easiest way to do this would be to think about, well, $31. I'm trying to think about how I got to the solution, but I guess the idea is like, we have 31 and 52, right? This would be relatively right? The problem is, for this answer, we got 31 and then 52 and then 38 and 77, right? Because we reverse this one, then reverse this one, then reverse this one, and reverse this one. But one thing to think about is, well, if you took this and you did it last, right? And then you flipped it, it would be in the right order, right? So if this was done over here and you reversed it, it would be like this, right? It would be 1, 3, 7, 7, 8, 3, 2, 5. Right, but things are now in the wrong order. So if you did this in reverse, right? If everything was done in reverse, meaning that you did this process, but you started at the end, what you'll notice is, well, if you just reverse this, then you'll get so we reverse this here. So 1, 3, 2, 5, 8, 3, 7, 7. You'll notice you get the answer here. Right? Because if each of the individual components are reversed, if you do it in reverse, then reverse it, you'll get the right order. Right? And there's probably a formal way that I could state that, but I guess what was intuitive for me was just like, okay, 13 becomes 31, it's backwards. So if it's backwards, if I put it in the back and then reverse, it'll be correct. Right? So that was more of like an intuitive observation about, like, if I reverse or reverse or reverse, then it'll be okay. But, you know, I think that's something that you kind of notice if you just printed it out and then thought about, okay, 31's, it's supposed to be 13, but it's 31, so it needs to be reversed. But it'd be easier if I just put it in the back and then reverse it at the end. I guess that's the best way to do it. You could also, like, append this stuff and then reverse it before you append it to your solution array, right? So another way you could do this is you could say, you know, S equals nothing. You could say S append this, right? And then at the end, you could say sol extend S reversed, right? And this would also work, but that doesn't seem as cool to me, right? Because each individual number, the digits corresponding are in the wrong spot. So if you reverse them before you append it to your solution, that would work as well. And maybe that makes a little bit more sense to you. So should I leave it like this? I don't know. Let's think about it. A little slow. So maybe instead what we could do is we'll look at the numbers in reverse order, and then at the end we'll return the sol in reverse order. So we'll reverse or reverse, and that should be a little bit faster. And now it doesn't work at all. Oh, because I forgot to drinking Henny turn me to a superhuman. Yeah. There we go. And then what we can do here is we can make this a little bit shorter, like that. And we got a 4-line solution. Makes us feel real nice inside. All right, guys, so what's the run and space complexity of this problem? Well, let's say n equals the length of nums. Okay. And let's say that m equals the max number. Okay? So the max number in nums, right? Now, for time, we have to look at all n numbers, right? So we have to look at all n numbers. But then for all n numbers, we have to find each individual digit, right? So to find each individual digit, it's going to be log of that digit. Log of that number, right? This number, right, is, let's make a simple example, right? If you had 9999, how many operations are you going to have to do on this number to find all the digits? Well, 4, right? Because you're going to have to look at this digit, then this digit, then this digit, then this digit. So that's the number of digits that there are. And if you think about that in terms of math, right? If you had, I guess a better example would be, if you had 1, 2, 3, 4. Right, so this is, you're going to have to do 4 operations, right? And this is 10 to the 3, right? That's all this is, right? It's 10 times 10 times 10. So you do 4 operations when it's 10 to the 3. What if this was 1, 2, whatever, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you're going to do 12 operations here, and this happens to be 10 to the 11. So what's the relationship between this 3 and this 4 and this 11 and this 12? Well, if you're familiar with some, fundamental mathematical concepts, and you learn in Algebra 2 or whatever, that's just log 10 of 10 to the 11. Right? So for whatever the longest digit is, you have to do log operations. That's what I'm basically trying to suggest here. Okay. So that means that you have to do n numbers you have to look at, and then you're going to have to look at log m digits, right? Because there's log m digits in each of the numbers in the worst case. Okay, and then what about space? Well, you have to make n slots in your array. Well, you have to make more than n slots because you have to look at all n numbers, right? And then there's log m digits for each number, right? So there's at most log m digits for each of the individual numbers. So then for all n numbers, there could be log m digits. So you need to make n log m slots in your array. So that's n log m time. All right. So this is one of those problems where maybe it's easier to actually do it and a little bit more difficult to analyze the runtime complexity. All right. That's all I got for you guys today, or tonight, or this evening, or this morning, this afternoon, whatever. Peace out.